right on Madison.
No, you get off the freeway.
Well, I live in McCall, so I'm coming down Eastern Valley. I'm gonna turn right on Madison, going back
Toward
Flying
Fourth
J.
Avenue, yeah.
Yeah, and then you get the bay and take a left.
So we talked about DC, AC, conductors, PLCs, loads. Y'all okay there? Of course, Ohm's law, Watt's law, Kirchhoff's law, series, parallel, circuit, color code.
Color code for what?
Well, well, no. We use these color codes for inductors. We use the color code for capacitors. The problem is most capacitors, they write the value on there, but then you get in these little old tiny capacitors. So these little old tiny capacitors, little tiny capacitors are rated in something called microfarads or picofarads. And those are the two standard units.
Where is that?
Is it the micro?
It's the color code.
Where is it?
It's the color code. It's the only color code you know. Brown, black, green, red. That's the color code. We use that color code for capacitors. We use that color code for inductors. We use that color code for resistors. It's still the same color code.
Oh, okay. Well, I didn't know.
So we call it the resistor color code, but it is
Same thing.
the color code. It's just that you got to learn what units they are because the multiplier varies with the units. So if you saw, if you saw brown, black, brown in an inductor, then that's going to be in millihenries, right? So that would be 10 millihenries. So it's in millihenries. So you have to know the unit that it's in. So capacitors are in microfarads or picofarads. They don't use the color code until it gets too small to write the value on there.
So is the whole microfarads one color?
No.
It's got rings on it.
Not microfarads. Microfarads are big enough to put the value on there. Where we get into problems is when the capacitor gets so small, they can't write numbers on it anymore. So instead of writing numbers, they put colors. So that means they're in picofarads. So if I saw brown, black, black on a side of a capacitor, I would say 10 picofarads. Right? You understand? If I saw brown, black on an inductor, I would say 10 millihenries. And of course, on the resistors, we say ohms or K ohms, right? You understand that? So inductors are rated in henries, but if it's color coded, it's going to be millihenries. Capacitors are rated in farads or microfarads or picofarads, but if it's color coded, it's going to be picofarads. Okay.
Which one of them is just a decimal? Is it a picofarad?
Picofarads. It's not a decimal, it's a number. And that's what I'm going to get out here and show y'all. So these are picofarads. They're not color coded, but they use kind of like the color coded method. So I don't know if my camera's still up. And I think I was using this guy. Full screen. And that's a picture. What do I do? Okay, this is live. So when I look at this, if it focuses it in, it's got 224 on it. What size is that? Picofarads.
What did you say?
224. Now these little bitty ones. Microfarads are big enough to write the value on there. So on microfarads, they're going to write the value on there. It's when we get into picofarads where they start getting very, very small and they don't have any room to write all the information on there. These guys are rated at 1,000 volts. That's their breakover voltage. So we know that. And then right there it says 224. So what size is that? Where's my PowerPoint?
Maybe.
Should I get something I can draw on, guys? I might have to put it on the board. Here we go. So what's for our 5-band resistors? What's its number of zeros? This is true. So it's number, but they give me the number. Instead of giving me a color, they say 2, 2, and 4 zeros. And so that would be 2,200 kilopicofarads. But by the way, on capacitors, we do not use, when we write them down like this, so this would be what? It would be 2,200, it would be 220,000 picofarads. So it's the same thing, but it's not a color code. So on these capacitors, they give, when they start getting small, they start throwing a bunch of numbers on there. And these are, I think these are all 20%. And they're rated at, they have a breakover voltage of 1,000 volts. So this is what they do. They give you numbers. 2, 2, 4. So that's 2, 2, and 4 zeros. Right? You understand? So, and these are all rated at 20%, and they're all 1,000 volts. These little, we call them ceramic capacitors. But if they get smaller than this, then what they're going to have to do, they'll go to a color code. And they're in picofarads. So like I said, if I saw brown, black, black, then I would say what? I would say 10 picofarads. But it's the same color code that you learn in resistors. I can show y'all an inductor. It's a little inductor. It's color coded, but it's an inductor. And so it would be in millihenries, right? You understand that? Yes or no? Where's my PowerPoint at? I must have stopped it. Oops, my PowerPoint. That shouldn't be up there. That shouldn't be up there. Should close that up. Where's my other PowerPoint at? I still got to close that out. Here we go. We've looked a little bit about diodes. We didn't get any time about transistors. And of course, if you take solid state, you'll take those. We talked about what makes up a control system: input, control logic, and then output. Right? We okay? Control devices. We looked at that. Looked at all these different type of sensors. Are we okay there? Huh? Well, you need to ask me. Now's the time. We have limit switches, proximity switches. Are you okay there? And then our non-contact, we talked about reed switches. We talked about magnetic reed switches. We looked at the way the pneumatic cylinders, or most of them are made now with a magnet on there, so we can use either a reed switch or a Hall effect to sense its position. Talked about Hall effect sensors. Then we talked about the photoelectric sensors, the through the beam, the retroreflective. Are you okay there? Huh?
Yeah.
Then we talked about, of course, the interrupters, which is a through the beam, but it has its own special name. So these are your transmitter and receiver are built in one unit. Talked about capacitive sensors and inductive sensors. Are you okay there? Okay. Talked about ultrasonic sensors. Are we okay there?
Hey, wait a minute, I'm telling you. Needed a little evidence here.
Pressure sensors. We okay there?
Yep.
In fact, that was the last class, right? We didn't do much about the RFID sensors, even though y'all run into these all the time. We talked just a little bit about those, right? Temperature sensors, we talked about the misters, thermocouples, RDTs, and infrared. We talked about that last class, right?
Question about that last. RFID, is that for radio frequency?
Radio frequency identification. Good. So we use RFID tag. What these RFID tags are is they're electronic circuits, but they don't have power applied to them. And what they do is when you walk through that sensor, it transmits an electromagnetic wave. And it works kind of like a transformer. So it's got a bunch of little coils of wire in there, and it works like the secondary of a transformer. So when you walk into that RFID sensor, it powers up the electronic circuit. And then the electronic circuit conveys information back to the sensor. Now, it could be very fundamental, which these guys hadn't paid for this. So you walk through these things all the time in Walmart. They got those blades on the side. Those are RFID transmitter receivers. And so they don't put batteries in those little tags that's on these CDs and all those other kind of stuff. And what they'll do is they either take the tag off, right off closed, or they run it across a little pad that puts out enough energy, it blows the circuit. It blows the fuse in the circuit. So now when you walk through there, the little fusing element is blown and it don't pick it up and it says you paid for your item. Right? You understand that? So those are RFID tags. They could put enough in, so most of the time on those, they just say, well, this guy hadn't paid for it, right? You understand? But they could send all type of information. So they have companies where these people just wear their ID bags on their belt and they walk through these two things and it says, I'm here. Right? And it clocks them in. So it can send all type of information on those little security cards, those little codes. What ours actually sends, we don't know. There's no documentation on it, but we got an RFID sensor on there, and those valve bodies that have the black circle on it, those are RFID tags. And we need to find some information exactly what that sends, because right now it's one of those sensors that is not in the PLC program. But we could do different things. So and that's right before it feeds the robot. So instead of using an inductive sensor to sense what it is, we could actually use that thing to sense the acrylics and sense the metal, right? For the ones that have it on it. So we're okay? Use electromagnetic electrostatic coupling in the RF frequency spectrum to automatically identify RFID tags attached to objects. Passive tags, which most of them are powered through induction provided by the RF frequency supplied by the RFID. Couldn't you imagine down at Walmart if they put batteries in all the clothes that's got those RFID tags on, and they'd have to come by every month and replace all the batteries in all the clothes that they sell. But so those are powered up through induction. So these are passive too, but they do have them which are active. So is that okay? Y'all understand that? Okay. Temperature. We have thermocouples, thermistors, and RDTs. Okay there? Solenoid. Y'all okay on solenoid? What's a solenoid? Solenoids are electromagnets. That's all they are. But they convert a current or electrical current into a motion, right? Solenoids, the motion is linear. It's a straight line motion. And then we have rotary cylinders. Okay. You heard. DC motors, DC and AC motors. This is what we covered last class. The different types of DC motors and how we reverse them. Are you okay? How we control the speed on them. Are you okay there? Talked about the shunt motor, the common source motor, the separate sided shunt motor. Talked about the permanent magnet motor, which is all the motors on our line, by the way, are permanent magnet motors. All the motors in your car except for your starter. Your starter is a series motor on your car. But all your windshield wiper motors, your lock motors, if you got a lot of your cars now have the radiators are instead of being ran off your engine, they're run off a motor. Cars are more the car is more efficient. It burns more efficiently. The hotter you let it get, it burns gas more efficiently. So used to, the fan was ran off your motor, but a lot of them now are actually run off. It's got a DC motor up there, right? You understand, that runs your fan, and they run it on a temp sensor. So what they do is they don't run your fan on your radiator until it needs it. So if you got a belt driven fan, that fan runs all the time. So that means in the wintertime, your heat probably comes on faster. So instead of blowing the fan through the radiator, even when it's really cold outside, they wait for a while and kick it in, right? By the way, most thermostat does, but the water doesn't flow, and that's your problem. On the thermostat, they don't let the water flow, and so that means you still have to wait till your thermostat kicks in before your heater works, right? Yeah, sometimes the thermostat would get froze open, and the problem is if it never warms up, your car is less efficient. So what we want to do is we want to run them as hot as we can without them burning up, right?
I got an 80-mile car, and it's 2 of them.
On the radiators, yeah.
In 1980.
And also on these real fancy cars, they might have multiple radiators on them because they want to make the nose really low on those things. And they'll have 2 radiators on each side, and they'll put vents coming in over the tires. So your air is actually fed over the tires into 2 radiators, just so they can make it real sporty looking. Those are DC. Those are permanent magnet motors. Well, every motor in your car is going to be a permanent magnet motor, except for the starter. The starter is a what type of motor? The starter is a series motor because we want a lot of torque because we're turning over that big engine out there, right? We got a series motor up there in the motor control lab that's pulled apart. How to reverse them? Normally we reverse DC motors by changing the armature. Unless it's a brushless DC motor. We have 2 brushless DC motors. One of them's called a stepping motor. Are you okay there? Stepping motors are really neat motors because they move precise steps. So we can run those open loop, huh? Very accurate, but it's got to find itself because if it's out there in nowhere, so when you turn that thing on, you'll watch that carriage move around and find itself. And then once it finds itself, then all it does is keep up with what? Just keep up with steps. You was doing that over at Just 8. Well, no, when you enter a 3D printer, you put all these dimensions in there. And then what it does is it translates that dimensions over to number of steps. And it's not hard to do because you know how far it'll rotate depending on your gears. You know how far it will move for each step. So we can gear those things too. So one step might be 1/1000th of an inch, right? And then you say, well, I want to move 15 inches. Well, all you have to do is take 15 inches or 15 millimeters, divide it by the step size, and then that will give you the number of steps. And so the motor would step those other steps. The motor don't care. All it does is and it's a motor. And what's the difference between an rotary actuator and a motor? That's a good question. It has a limited stroke. A motor doesn't. So I mean, you can move that thing as far as you want to, and it'll just sit there and run. So all you have to do is know how it's geared. So know how far your output moves per step, and then just do the math. So say I want to move this 10 inches, then you say 10 inches divided by so many inches per step. Do the math. Come up and say, well, that's going to be 50,000 steps. The motor would just step 50,000 times, and how many rotations that would be, and it's real precise, isn't it? So a lot of 3D printers use stepping motors. In fact, the one that Thomas Hickenbotham, he's here. in y'all's program, he makes 3D, he designs and makes 3D printers that prints with the wax cord, not the wax cord, the plastic cord. What type do y'all have? Breathe cord? Yep. The one they got over there they have a silicone or a sand printer over there in Grafton. And what it does is it puts extremely thin layers and it squirts glue out. Whether that uses a stepping motor, I don't know, but odds are it does. I mean, that's the perfect motor to use in something like that. And then we have the brushless DC motors. These are used in, where we don't need slip ring. Those commentators. Those commentators generate a lot of electromagnetic noise. And computers don't like noise, right? Digital stuff don't like noise because all it takes is make a 0 or 1 or a 1 or a 0 and everything could go out of whack. So any motors that's inside a computer, these are going to be brushless. So all the fan motors and everything inside the computer are brushless. AC motors, we looked at shaded pole motors, we looked at single phase motors, and 3-phase motors. Are you okay there? So remember, single phase motors we have to create a shifting field. So we either do it by what? We do it by capacitive start, capacitive run, which is a capacitive start, but we just call it that. A split phase. So these use capacitors to create a phase field. The split phase uses inductors to create inductance to create a phase shift. And then the shaded pole motors use those shaded poles, right? Are you okay there? Didn't have enough time to get into the type of 3-phase motors, but we talked about that in motor controls. So we have Y, we have delta, and if you get a motor, it's up to the manufacturer. From your point of view, on a Y motor or a delta motor, it makes no difference. It's the manufacturer, how they do it. But when you get into these motors, these Y delta motors, that's where it starts making a difference. What we're trying to do, we get into these extremely high horsepower motors, and as a rule of thumb, y'all remember what's the starting current on what's the rule of thumb starting current for a motor? Rule of thumb starting. So y'all know, is the starting current going to be more than the run current, or is it going to be less? A lot more. And what's the rule of thumb?
It's a percentage.
Not a percentage. Not twice.
No, it's more.
Yeah, 6 to 8 times.
That's
It's not a percentage, it's a multiple. 6 to 8 times, and that's if it's not given, right? You understand that? 6 to 8 times the full load current. And the full load current is what? What is the full load current? What is the full load current? You're talking voltage and I'm asking about current. What's the full load current? That's the amount of current the motor should draw if it's running at its rated voltage, at its rated horsepower. So if you got a 5 horsepower motor that's supposed to run on 240 volts, if you put 240 volts on there and you make it run 5 horsepower, it's supposed to pull that current. So the full load, so it's rated horsepower, right? You understand that, at its rated voltage. And that's what's on the plate. So it don't give you the starting current. Usually it gives you a letter. You'd have to look it up on a chart. I wish I had the chart for this class. But a lot of times it'll give you a class, like class A, class B, class C. And what that does is you look that up on the chart and it would tell you the multiple of the starting current. So all class A motors would have a multiplier for the for the starting current. And the bigger the letter, the more it's going to pull. But rule of thumb, if you don't have that information, rule of thumb is 6 to 8. And of course, what I would probably use is 8, right? Because that would take into consideration.
Isn't that not 6 to 8? Isn't that
No. The only thing that's on your nameplate is FLC. Or it might be FLC. Most of the time now what they put on the nameplate, is they put amps. And then they'll put a number out beside that. And they don't put a unit because they got amps beside that. What is this? Well, this is the full load current. That is not the starting current. And what is the full load current? What's the full load current? I'm going to put that on this. What's the full load current? Well, that's not what it runs on. That's when it's running at its rated voltage at its rated horsepower. So if I got a 5 horsepower motor and I'm running at 2 horsepower, it's not going to pull that current. Right? You understand?
No.
So that would be like I've got a car that's got 350 horsepower out there. How often are you going to release that 350 horsepower? So they rate it at its maximum horsepower. But it don't mean you got to go 350 horsepower unless you're a drag racer, right? You understand that?
But most of these motors, they run. You keep the motor.
That's right. You're supposed to. But what happens but you can't say I'm going to always run 5 horsepower. So when you size a motor, you size it for the maximum load it's ever going to carry. You don't size it for the average load. You size it for the maximum load. So I've got a conveyor belt and it's running all these different things out there. What's the odds of that motor running at its rated horsepower all the time? Very, very low. It's just what's the odds of your motor running at its rated horsepower on your car? What's the odds of your car running at its rated horsepower all the time? Slim to none, unless you're a drag racer. A drag racer, huh?
What's that test question again?
So what is the full load current? So when you buy a motor, what are you going to usually buy? You're probably going to try to buy a motor that's going to carry a multiple of your maximum load. So you don't want to carry the maximum load. You want to carry a multiple of that, right? You understand? So odds are the motor's going to be running under its rated horsepower. So odds are it's going to be pulling less current than what's on the nameplate. Because that nameplate is what we call full load current.
Don't they have to say, if you were going to put one in, wouldn't you have a safety factor?
But that's you as an engineer. All the motor gives you is its full load current. The motor don't give you a safety factor. It gives you the full load current, which means if you're running that motor at the rated horsepower, at the rated voltage, that's it you can get. If you try to get more than that, that's not true. We have another thing on the motor called the service factor. Not service, Richie. So what's the service factor of the motor? It's how much you can safely overload the motor. And they're not big either. Maximum I've ever seen is 2. You see a lot of 1s. If you see a 1, that means you can overload it, right? You understand? So if it's got a service factor of 1.25, that means I could take my full horsepower and multiply it by what? 1.25. So that's on the motor, but that's on the nameplate. So what's on the nameplate is your full load current, your service factor. The service factor is how much you can safely overload the motor, right, without burning it up. You have a frame type, which tells you how the frame's put together. So a frame type means if I want a 1 horsepower motor, all I got to do is make sure it mounts in the same slot. You can either buy it from the company that's on there, or you can find one that's got the same frame type and the same horsepower rating and full load current. You can buy the dang thing from anybody. So it's a NEMA, National Electrical Manufacturers Association. So this is the guy you want to look for, NEMA. NEMA allows you to register open standard frames. So NEMA is mechanics of electricity. So that plug over there, that's mechanical, that is a NEMA 20 plug. So it's rated. So it's NEMA 20 means it's a 20 amp plug. I'm sorry, it's not NEMA 20, it's a NEMA 5, NEMA 6. So they assign numbers too. So a NEMA 5 is a 15 amp plug, a NEMA 6 is a 20 amp plug. But if I go out, if my appliance says it needs a certain plug, they're going to give me the NEMA number and I can go out and buy it, right? You understand that? So they give me and so NEMA sets up the mechanics of things. So the layout of that plug. So if you go over and look at that plug, it's got a little blade on the side of it. It'll be different than the plug you got in your house. So that was established by NEMA, which allows a 15 amp device to run off a 20 amp plug. But if you buy a 20 amp device, it's going to have a blade. So one of the blades are going to be like that. And that will only plug into a 20 amp plug. So it's okay for us to run a 15 amp device on a 20 amp plug, but you don't want a 20 amp device on a 15 amp plug, right? So people will cut off that blade too, by the way. They'll say, well, it won't fit in the plug.
I've never seen that.
Huh?
Hey,
Well, it'd be hard to force that in because if you go over and look at that plug, that blade is well defined. And it goes on up. So what it does is the blade is offset to the side, and it goes up. So a 20 amp cord would have that on there, and a 15 amp cord would have that on there. So it would plug into this slot. The 20 amp depends on that little cut thing on the side. You can't force that in there. If you force that into a 15 amp plug, you're gonna break it off. But you could cut this little well off there, right? You understand? And then try to run a 20 amp device on a 15 amp plug, which is not good. It's going to pop your breaker all the time. You go in there and keep resetting, and eventually you're going to burn some stuff up. Coal miner, man. So those times go. What's else on the motor nameplate? So what is the full load current?
Full load current.
Frame type. It's going to be a type. It's going to have a number out there, and it means any motor that's got that same frame type will be able to mount in there, which means it has the right foot, it has the right height, it has the same shaft lengths. All that's inside the frame type. So the frame type is on the nameplate. The full load current is on the nameplate. The service factor is on the nameplate. The insulation class is on the nameplate, which would basically tells you the full load current capabilities. It's going to give you a multiplier. That's on the nameplate. So it don't give you the full load current, but it gives you a letter where you can calculate the full load current. I'm sorry, the start current. Gives you the voltage that it's designed to run off of. And sometimes now they give you the efficiency of the motor. That's required on motors now. So efficiency means you running that thing at a rated horsepower, and you take the voltage and the current that it's pulling, right? You understand that, and then rate that to what it's supposed to pull, or the horsepower it's supposed to develop. So it's supposed to develop. If I put 100 horsepower worth of power in, it's supposed to develop 100 horsepower worth of power out. What's the watts per horsepower? 746 watts per horsepower.
Go ahead first.
So if I've got a 5 horsepower motor, I could multiply 746, and then I come up and it measures 10% above that, then that would be the efficiency of the motor. So actually it's pulling more current than the horsepower it's developing, right? You understand that? Yes or no? So now they put that on the motor. They put the on these new motors, they'll put the efficiency of the motor, and they'll also put a power factor correction on there. So you'll know what size capacitors to increase the efficiency of the motor. But well guys, that's it. So that's